Hey guys, Mr. Backerberg here. In this video, we're going to look at how differentiability implies continuity. So if your function f has a derivative at x equals a, then the function f of x is going to be continuous at that x value of a. And we're going to go through and prove that the limit of f of x as x is approaching a is equal to f of a, therefore proving the continuity. Now to prove this, I'm going to do a little rearranging. I'm going to subtract the f of a over to the left-hand side. So then we're looking at the limit as x approaches a of f of x minus f of a, and we're going to prove that that's equal to 0. Now, in order to help me prove this, I need to do a little multiplying. I'm going to multiply by a fraction x minus a over x minus a times this f of x minus f of a. And that's going to let me do a little rewriting. I'm going to take this x minus a that's in the denominator over here, and I'm going to write it as x minus a times f of x minus f of a all over x minus a. Now, I do want to remember that I'm still doing the limit of all of this stuff as x is approaching a. And one of the properties of limits says that if you've got multiplying happening, you can split that up into two separate limits. So we're going to do the limit of that first piece, which is just the x minus a, times the limit of the second piece, which is actually that alternate definition of a derivative that we looked at in an earlier section. Now, as we're evaluating each one of these limits, this first limit we can do using direct substitution. If I were to plug a in for that x in there, we would get a minus a, which is just 0. And like I mentioned, this is the alternate definition for a derivative. So this whole second limit really just turns into the derivative of f at a. So now if we're multiplying these pieces together, we said that the first piece was 0 and the second piece was that derivative. Well, if you take 0 and multiply it by anything, you always get 0 as the answer. We were trying to prove that this was going to be equal to 0, and we just got 0 as our answer. So by showing that this limit of our function f of x as x is approaching a, showing that that limit is equal to just f of a, implies that this graph is continuous at the x value of a. Now, it doesn't necessarily work the opposite direction. Continuity does not imply differentiability because we've seen lots of continuous functions that are not differentiable for different reasons. Remember, one reason could be if there's a corner in your graph, or there could be a cusp in your graph, which looks kind of like a corner, but it's a little bit more rounded, or if your graph has a vertical tangent line. If any of those things happen at a specific a value, then your function is not differentiable at that a value, even though it's continuous there. That's going to be it for this video. Thanks for watching.